equating the real part of L1 with real part of L2. Okay, and we can write down the asymptotics on those two regions. So they involve n to the 2/3, and you go back to the plain partition numbers that I gave earlier in the talk. The power here was n to the 2/3. Okay. So the third basic example I had were the odd partition polynomials. Right. So I try to do everything with degree 1,000, so you don't see much there. So 900, you do see there is some separation there. So that gave some, that was first numerical evidence there is something there. So for the odd partitions, there's this little curve, as I said here, the number I. And that's a close-up of it. Right. And again, for this case, the zeros populate these curves very slowly. Right, so the recurrence for the odd partition numbers is naturally used powers of 2, so I just went up from 2 to the 12th to 2 to the 15th, which is 32. You probably have it better memorized all the digits than I do, so roughly 32,000. Okay. So we see that even with those high degree polynomials, it's a very sparse family, right? And so the asymptotics are described with functions which are similar to the original partition polynomials. So there's a distinction between even and odd. So for the odd index, it's exactly what I had before. For the even case, so instead of having 1 over 2j, I have 2 over it, and then I have minus x to the j. So the level set for the attractor involve setting real part of L1 equal to the real part of L4, and real part of L2 equal to the real part of L4. Thanks. All right. So I do have some time, so I can indicate how these asymptotics come about. So I'll focus on the original case with partition polynomials and look at the indicate how the circle method can be adapted. So we start with the
type of times q to the power n, right? Is a sigma.
Yeah. I have a product.
You're missing q to the n next to the fn.
Okay. Yeah. Yeah. Okay.
It's implied.
Yeah. Right. Yeah, I should. Yeah. All right. So. Okay. So the circle method the name comes about from applying the Cauchy integral formula to the generating function. So just take the generating function and to. I forgot that.
Yeah, but I told you.
Yeah. Right. So I want the power of q. Right. So I need to add. Right. So I need the coefficient of q to the n over here. Right. As you indicated. Right. So that would be get that by taking the generating function and integrating the function against du to the n plus 1. Okay. and you do it along some circle with radius inside, with radius less than 1. Okay? So there are a lot of similarities to these generating functions with x fixed, so one has to be careful. So what one does then is going to classical circle methods divide the circle into subarcs relative to rational points distributed around the unit circle, and use the device so-called Ferry fractions, which are just the rational points along the circle. So Ferry fractions, you just look at fractions, and you're just highlighting the biggest denominator. And there's special intervals that you get from the Ferry fractions. So there's only in these intervals, there's only one Ferry fraction that lies inside it. And then all the corresponding arc psi. And decorated by these indices, HK, that's the typical notation rather than the actual fraction. And capital N indicates the degree of the so-called order of the Ferry fractions. All right, so to apply the Ferry fraction in the circle method, both the radius of the circle will approach 1, and the order of the Ferry fractions also will depend on the degree. Now, since we're evaluating polynomial, these will also depend on the evaluation x. So radius of the circle is given in terms of this formula, so it depends on where we have choose x inside the unit disk in which of these regions. All right, so to start the method, you really have to know the end result because you putting the radius in terms of region. All right. So it turns out in these arguments that not all the arcs have equal importance, and usually just one arc will persist as n runs off to infinity, and that's the so-called major arc, typically. Okay. Now, in order to apply the circle method, I have to somehow ferret out the major contribution to these limits out of the generating function. So what we do is, right, so I just do it. So, right, so we take the log of the generating function. Now we're interested in, since we want to get good control of the integral along in a neighborhood of a rational point on the circle. So the rational point in the circle would be e to the 2 pi I h over k, right? And I want to point near it. So I have this minus w, so I get a neighbor to that point. So to get inside the unit circle, since I have a minus sign there, I take the real part to be positive. Right, so I work do some work. All right, so however many months it took. So you look at this, and it turns out this is a pretty cool way of getting control of the generating function in the neighborhood of a rational point. So in this expression, where we introduce these functions q, h, k, and we just do a series expansion. So we do a series expansion, and we get a function that looks like this. So it's a double series in M and L. Here I have an x, looks like this will be a so-called polylogarithm, and then I have something else here. So of course, if this were 1, then I would just have a zeta function. Okay, so I'll say what they are explicitly if I have time. Okay. Now, to get the dominant term, so I should say this formula for the exponential that I use is good for a vertical line, which is to the right of 1, real part 1. And what standard thing to do is to shift this vertical line from real part 1 to the past 0. So when we do that, there'll be poles of Q. And what turns out to be the case is that the pole at 1 will give the dominant contribution. All right, and to get the residue of that pole, I need some useful form for this auxiliary function I introduced in the neighborhood of the generating function at the rational point. Okay, so write down the useful formula for Q, capital Q H K. We just write down this list of special functions. So I have the polylogarithm. So we already saw this when S is 2 the die, logarithm 3 the trilogarithm. The zeta function comes up. If I have time, I have some other examples involve the zeta function as a Horwich zeta function. And what comes up is, this is sort of the most general situation, so-called Lurch phi function. So notice if you would set Lurch phis, if you set, say, a to be 1 and x to be 1, you would get zeta. If you set a to be 1, then and keep the x, then you would get the polylogarithm. So the Lurch phi is sort of a master function. So using the Lurch phi, you can get a closed form expression for this QHK as this finite sum. So we have a term here that involves a zeta function and polylog and these additional terms. So to get this, all I do is take the what I do is simply take the index L and just split it up according to the residue classes modulo K. And just use this list of special functions and you get this formula. So it's just a simple version, so nothing profound. But lots is known about these functions, so it's useful. So so the only contribution to 0 is, in terms of pole, is from the zeta function. So we know that the Riemann zeta function is, has only a single pole in the complex plane and occurs at 1 and has residue 1. Okay, and this is all good stuff at 1. Okay, so this has residue 1, so I can set S to be 1. So now if this becomes a k squared, then I get the polylog. The polylog then becomes a dilogarithm. And I have x to the k. So I have this formula. So that's very nice. Okay, so I have
5 minutes.
5 minutes, okay. All right. Now another feature which is independent of this, so these are methods from classical analytic number theory, is a fact that would be a subset of complex analysis. So we have to know, so when we do the circle method, we just don't have a priori denominators of 1, 2, 3. We could have, right, so arcs, the denominators are going off to infinity, so we could have arbitrary order denominators, the order of the Ferri fractions. So to rule that out, we need the following theorem that involves the domination of the real parts of the family of functions, 1 over k, the square root of the dialog of x to the k. So it turns out to be the case that the real part of Lk for k 4 and larger is dominated by the first 3 terms of that sequence. All right, and there's a corresponding theorem then for the other cases. All right, so the reasons I introduced earlier then, was comparison among the first 3 terms of that sequence. So there's a stronger definition for it, is that if m is either equal 1, 2, 3, then that region, really the real part of Ln then dominates all the other terms of the sequence. That's just one, not just the other but say 1 just not only does it dominate 2 and 3, but also all the rest of the terms. All right. Then, so we go back and look at the integral of the generating function and apply the Cauchy integral formula to it. Then doing some work, we get an integral of this form. Where inside the exponential is this function built out of the dilogarithm. So, and this is formulated under the restriction that x is in Rm. Then one can apply saddle point method to understand the asymptotics of the integrals. And it turns out that there's one saddle point that occurs at minus the imaginary part of Ln. And when one puts that into this formula, all right? So I guess the major part here I want to say is notice this has a square root in it. So when I'm doing the analysis, I have, oh, well, where does square root come from? So it comes from this part of the analysis. Okay. So that will give rise that I can analyze these integrals and doing work, I can put it all together and establish the asymptotics of the polynomials in the original case. Okay. Now, one can apply this. So to apply these methods, a lot of it can be, it's very mechanized then in terms of generating function. But there's a bottleneck in terms of getting complete theorems is that you need this domination theorem. You have this sequence of analytic functions, and you have to be able to compare real parts of that sequence. So that's the bottleneck. There's not a good, that's not something I can just go off the shelf. All right, there's theorems. But if you believe that, so I mean numerically, this comparison theorem for harmonic functions is very easy to verify numerically. So you believe that, then you can do lots of going the wrong way. So I just had fun the past week or so. So here I had partitions, polynomials for partitions with parts congruent to 1 or 2 mod 3. So I then just went through. So these are just plots of zeros. So then I the zero tractor, and you get these. So this is what the functions look like. So you get something a little more complicated. So you get in terms of the just to plot or solve it, do anything. So the large phi function comes in, and you have these roots of 1 come up into play. So I just had fun doing lots of them. So 0, 2 mod 3. So as I said, I get these complicated functions. So these would all be correct. These would be theorems if I would have to compare this sequence of harmonic functions, and I would be able to know when one is larger than dominates all the other terms of the sequence. All right. So it seems like it's a very, very nice method, and it's bottleneck from complex analysis. So I'll stop.
Thank you very much. We're going to be glad to answer questions in private. And if you'd like to join us for dinner, please let me know right now. Thank you. 6:45 at the latest. It's beautiful pictures. It's perfect talk for measurement.